We want to determine if each sequence converges or diverges. If it converges, determine what it converges to. To do this, we'll treat the formula for the terms in the sequence given by a sub n as a function of n, and determine the limit as n approaches infinity. If the limit exists and is equal to L, the sequence converges and converges to L. If the limit does not exist, the sequence diverges. For the first example, we need to consider the limit as n approaches infinity of the square root of the quotient of 4n squared plus 1 and 24n squared minus 3. From here, we'll use the limit property to state the limit of the square root of the quotient is equal to the square root of the limit of the quotient. So we can move the limit inside the square root and determine the limit of the rational function to determine the original limit. And now to find the limit of the rational function, we'll use the shortcut by comparing the degrees. Notice the degree of the numerator and denominator are both 2. When the degrees are equal, the limit as n approaches infinity equals the ratio of the leading coefficients, which would be 4 divided by 24, which simplifies to 1/6. And therefore, the original limit is equal to the square root of 1/6, which equals square root 1 divided by square root 6, or 1 divided by square root 6. If you are required to rationalize the denominator, I'll also show that. We would multiply the numerator and denominator by the square root of 6. We can also express the limit as square root 6 divided by 6. The important part here is the limit exists and is equal to square root 6 divided by 6, which indicates the original sequence converges and converges to square root 6 divided by 6. If we look at this graphically, to show the sequence, we can graph points on the coordinate plane in the form of n, comma, a sub n, and now we'll plot the first 50 points, where again the y values would be the terms in the sequence. And we can see the y values quickly converge or approach one particular value, which we now know is equal to square root 6 divided by 6. And now let's look at the second example. This one's a little bit different because of the negative 1 to the power of n. This is an alternating sequence, so we'll use something called the squeeze theorem to determine the limit of a sub n. Notice all the terms in the given sequence given by negative 1 to the power of n divided by, let's write 5 times the cubed of n as 5n to the power of 1/3. All these terms would be greater than or equal to negative 1 divided by 5n to the power of 1/3, as well as less than or equal to positive 1 divided by 5n to the power of 1/3. And now we'll consider the limit of negative 1 divided by 5n to the power of 1/3, and the limit of positive 1 divided by 5n to the 1/3. If we get the same value by the squeeze theorem, the limit as n approaches infinity of a sub n would also be the same. So now we'll consider the limit as n approaches infinity of negative 1 divided by 5n to the power of 1/3, as well as the limit as n approaches infinity of positive 1 divided by 5n to the power of 1/3. Notice in both cases, we have a constant in the numerator, and because of the n to the power of 1/3 in the denominators increase without bound as n approaches infinity, and therefore both values of the fractions will approach 0, one from the positive side and one from the negative side. Either way, though, both limits are equal to 0, which means we can also conclude the limit as n approaches infinity of the original formula for a sub n also equals 0, which indicates the sequence converges and converges to 0. Let's also look at this graphically. Again, we'll plot points on the coordinate plane in the form of n, comma, a sub n. And for this sequence, which alternates, we'll plot the first 100 points. And we can see from the y values, the terms in the sequence are getting closer and closer to 0, which we also know from our limits. We know the terms are converging to 0. But the terms do alternate sign. I hope you found this helpful.